Well, welcome to the physics video lecture. Once again, it's physics 105A video lecture 24. We are in the middle of summing up a Fourier series, and I'll just remind us what we had here. So our function was just a step function. So between minus pi and pi, it was -1 over on the left side, +1 over here. And we wanted a series expansion. The technique is to expand in a trigonometric series. Right now we're just seeing the exponential functions. So we have c sub k e to the I kx, but k runs through all of the integers. And the coefficient, c sub k, and this is where we had ended. We had just done this integral. And what did we have? And then f of x e to the minus I kx dx. So we had just found these c sub k's. And what we have was 1 over 2 pi I k. We had a factor of 2, and we have 1 minus e to the I k pi. And those were 0 when k is equal to 0, plus minus 2, 4, etc. And we're going to have a -1 here, so 1 minus -1 equals 2 when k was plus minus 1, plus minus 3, plus minus 5, and so on. So when we had the odd integers. So what this turns into, and yeah, I'm going to leave everything in place here. So we're going to get a 2 from here, so we're going to have 4 over, and I have a pi times k times 2i. Okay. And that is for, like I said, k is the odd integers, and so on. So what we have to do is take these values of c sub k and plug them in here. And then all will be revealed. So it's shown right here. And I had pointed out that these things show up pairwise, okay? So what we're looking for is c sub k e to the I kx plus c sub -k e to the minus I kx. Okay? So they show up pairwise. And in our case, we have room right here. We have 4 over pi times k. Now the 2i I'm going to hold on to because it plays a role. So we have e to the I kx. Okay. But for the c sub -k, we have a negative sign out of this one. So if I factored it out, I have a minus e to the minus I kx. And I had that 2i left over. This here you're supposed to recognize as being the sine. Okay, the sine of k times x. So I'll just put here as in case you hadn't seen that or remembered that. You know, when we have the imaginary part of z is z minus z star over 2i, right? And for Euler's formula, the imaginary part is the sine. So yeah, make sure you recognize and know this. That's the sine, and we have equals 4 over pi times k sine of kx. So now we're going to write this big summation here. And I'll just write down what we get when we do the sum. So now f of x equals, I'm just going to write here odd integers, and I'll have my 4 over pi times k sine of kx, but I already took care of the minus one, so positive odd integers. Now we can turn this into a compact form as follows. What we're going to do is sum from n goes from 0 to infinity with the integers, and we'll have the 4 over pi. Now the odd integers of k will be a 2n plus 1. Okay. 2n plus 1. N equals 0, we have 1. N equals 1, we have 2 times 1 plus 1 is 3, etc. So 135. And then we have the sine of 2n plus 1 x. So there's the compact form of that step function. But we're not done by any means. Now we want to actually look at a few terms of this series and understand it. Okay. But yeah, we've done all the work. There's the answer. This here describes this step function, and then of course it would periodically continue from plus minus infinity. So let's put a box around here. What we're going to do next is write out a few of these explicitly and then graph them. And I think I'll use this part of the board for the moment. Now we'll send this up. We can do a much larger version. Okay, we really want to focus on this. So I'll draw the graph on the left side and I'll write out our function here on the right side, or vice versa. Let's see. So if we just write out 3 of these, we'll actually see what's going on very nicely. So we have f of x equals 4 over pi sine of x. Okay, that's the first one. And then we have 4 over pi, and then we're going to have sine of 3x over 3. I'm going to go ahead and keep this 4 over pi separate, so we always have 4 over pi sine 5x over 5. That we can try to sketch. After that it would become difficult. And the thing about this 4 over pi, this is slightly greater than 1. And that plays a role as well. So let's go ahead and let's see. We'll do our graph right here. Okay. This is a big one. For you guys, it's a half a page filler. Okay, so let's see. 1, 2, 3, and pi. Minus 1, minus 2, minus 3, minus pi, and then plus and minus 1. So we're actually going to try to do this scale. And since we have pi right here, and minus pi right there, then we know that pi over 2, just over 1.5, so pi over 2. And then minus pi over 2, minus pi. And 1 and minus 1. How about a little dotted line action? So how does this work? Well, let's just take them one at a time. I'll probably do them in different colors. So our 4 over pi sine of x. Now what's 4 over pi? It's a little bit more than 1. So I'll do this here. To make things not as confusing. But what do we have for the sine? It's going to pi over 2. So we're looking at this function. That's supposed to go up to pi. There's our sine here, and on the other side, likewise. Okay, starting to look like our step function. Well, maybe not. So now we have 1/3 of this 4 over pi, so we'll just look at about 1/3 of this. Third of this 4 over pi. And we have sine of 3x, so we have to go through, we have to divide this interval up into 3 parts. We're going to eyeball it. And there's the amplitude, so we're going like this. Wrong one. Okay. Out to here, so going something like this, and this, and that. Okay. Same on this side. I'll just kind of wing it. Okay. So we're adding my big curve here and this little one, and we'll do one more. We have to divide it into fifths. Maybe I'll use a different color for this one. This is kind of harder, but we're just gonna 2, 3, 4, 5. We'll just focus on the right side now. And now we're going and divided by 5, so it's much smaller. So now we're adding 1, 2, 3, 4, 5. So if you had a program to add all these numbers, you could do it, but let's go ahead and just try to recognize what's going on. You see at the beginning, all the numbers are adding in phase, so to speak, and so it's just becoming steeper. So it comes up steep. Comes up steep. Now, this second one, okay, the sine 3x over 3, looking at this one right here, this one was subtracting from the top, and the other one was adding a little bit. So you're going to start getting some wiggles here. Okay, you get a subtraction, and then a subtraction and addition. So here at the end they add again, so it's coming down steep. Okay. Now the rest I'm just going to kind of do free form to give you the idea what's going on. Namely, it's going up here and it's doing a couple of wiggles and coming down. Same on the left side. And the more of these terms you have, so if you took your 4 over pi sine 7x over 7, it will keep flattening these out till eventually, here's where I really need another color. Yeah, eventually you're going to get something, there's always an overshoot. Okay, something like that. The more of these you add. Yeah, there's a name for this overshoot here. We're not going to go there right now, but in the limit as n goes to infinity, this becomes continuous except at this point here. It goes through the origin, goes up arbitrarily steep. You can be arbitrarily close to the axis here, and then it will be arbitrarily flat and all the way down. And what's interesting is this mathematical technique can be used to construct step functions. Let's draw a step function once more, just the pure one, so we're not distracted. You can construct functions like this. Okay. Say out of wavy functions. If this were not x, but if this were not position but time, you could construct step functions out of these infinite series of frequencies. You would not have infinitely many. You would have some finite cutoff, and this is what your function generators do. So if you're ever in the lab, the electronics lab, you got a function generator, you have square waves, you have zigzag waves, sawtooth waves, things like that. If you zoom in close enough with an oscilloscope, you'll actually see some of this structure here. Okay, yeah, this is a huge topic. Fantastic. So now we have a complete example of a Fourier series. And so, yeah, have a good look at this graph that we constructed, play around with it yourself to see what's going on. It'll become arbitrarily smooth. Good. Consult the clock here. So now I want to assign one problem and then start generalizing this, because it's not enough just to know this complex form of the Fourier series. You'll notice we did get our real series out of it. There are also real forms of the series, and instead of minus pi to pi, which is what we started with, we can generalize to a symmetric interval minus L to plus L. So we're eventually going to know all that stuff. But what we did here was just the key to everything. Okay. So let's revisit the original expression. What you did see here was how adding these things, you know, they appear symmetrically on either side of the sum, adding them up revealed that we had a real function, okay? So there's also a way to go straight to the real Fourier series. That's what I'm going to talk about next. So we'll put the formulas back up on the board and pursue that. So once again, Fourier series. Now that we've done one of them, I'm going to do one more thing while we're on the subject. Let me revisit this. This is an example that I was going to tell you about what interesting materials contained in that series. So the step function that we could express as, f of x was sum over n, 0 to infinity, 4 over pi, sine of k. No, it's right in terms of n. Sine of 2n plus 1 x over 2n plus 1. And just to have it in front of us, minus pi, minus 1 here. So here's our step function. What about its value at pi over 2? F of x equals pi over 2 is, of course, just equal to 1, right? Right in the middle there. That's a safe bet that that's what it's equal to. And now we have this series here. We have 4 over pi sine of 2n plus 1 times pi over 2 divided by 2n plus 1. And we know this 2n plus 1 is just 1, 3, 5, 7, 9, etc. What about the sign here? 2n plus 1 times pi over 2. Okay. So this is the sine of pi over 2, sine of 3/2 pi, sine of 5/2 pi, etc. And if we remind ourselves, even we could just use the unit circle, it's going to be +1, -1, +1, -1, which just alternates plus and minus 1. Yeah, alternates plus or minus 1. So let's do this. So 1 is equal to 4 over pi times 1 minus, we're going to have the -1 and then the 3, 1/3 plus 1/5 minus 1/7, etc. And what you'll see is we've just discovered an infinite series that sums up to pi. Continue that. By the way, you'll discover it doesn't converge that rapidly, but let's have a look. So what do we have here? Pi is equal to 4 minus 4/3 plus 4/5. Or we could say pi over 4, keep things a little cleaner. So pi over 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7, etc. And if you ever look up this type of thing in a mathematical handbook, you can find many, many expressions for pi and various powers of pi that are some kind of infinite series, and now you know where those expressions come from. You could play around with this and construct different functions whose value is well known, is clear at a certain point, and where your trig functions are just giving you alternating ones and minus ones and zeros. And then this is what you'll get. So yeah, pi over 4. Try it out. It's going to take more than just these few to get any good approximation, but this is an infinite series, and the whole proof of it follows all the way through to here. Okay, so that's an important note. Yeah, put some words in there as far as what we've just done. All right, consult the clock again. Okay, so now I want to talk about the real Fourier series. So I'll go ahead and write this down. So we have, Fourier, capital F. So continuing with these, we have what we've just been studying, C sub k, k from negative to plus infinity, all the integers C sub k e to the I kx. This is really the clean form, and eventually you can almost see it in your mind's eye. You can turn this into an integration, okay, which we'll do. So with our coefficient, C sub k is equal to 1 over 2 pi minus pi to pi f of x e to the minus I kx dx. What about, and we saw, we had the real numbers come out of this. So next, the real series, f of x is equal to, and I'm just going to write down the form of it. you write a0 over 2 plus k equals 1 to infinity a sub k cosine of kx plus the sum k goes from 1 to infinity b sub k sine of kx. And it's possible to start with this and end up with this right here. Yeah. That's not only possible, it's not difficult with a sub k is equal to 1 over pi integral minus pi to pi f of x cosine kx dx b sub k equals 1 over pi sine of kx dx. And there are times when this way of looking at it is easier to use than this way right here. In fact, we could have done the integration we just did using this form here, and maybe I'll put that on the homework. But first we would want to prove these formulas. They actually follow directly from this here. Okay? They follow from this form. And I'm tempted to assign that as a homework. Here, let's send this up and think about it a bit. I think the first thing we could do is just repeat the example I did. I'm going to write down a few statements that are true about this, and then we can either solve them all on the homework, or I can do them, or we can do them together, or something like that. Okay. So this, like I said, this formulation follows directly from here. And what I want to do is add a few things to this. A couple of important notes. If f of x is an odd function. Now remember what an odd function is. That means f of minus x is equal to minus f of x. Okay. And what is an odd function? Well, that thing that we just did, our step function, was an example of an odd function. Okay. So if f of x is an odd function, I'll write here parenthetically example, little exclamation point, this one right here. Then all of your a sub k's are equal to 0. So then a sub k is equal to 0 for all k. And the reason is that if you have an odd function, cosine is an even function. So when you multiply the cosine times that even function, you're getting an odd function. And when you integrate that odd function from minus pi to pi on that symmetric interval, the left side is equal to half. The left side integral is equal to minus the right side integral. So it's kind of a trivial proof. I just gave it, and or you can go in there and prove it rigorously. But that's an important point, and if f of x is even, which means f of minus x is equal to, f of x. So if it's an even function, an example of an even function would be, that little symmetric pyramid there, equal on the left and the right side. Then all of your b sub k's are equal to 0. then b sub k is equal to 0 for all k. So yeah, if you're doing even or odd functions and it's a real function, it can, under circumstances, be much easier just to go straight to this formulation, because you, for example, the one we just did, you can ignore all the a sub k's, just do the sine kx dx b sub k. You know what, let's put that as a homework. F of x equals, I'm just saying the step function again, minus 1 minus pi less than x less than 0 plus 1, 0 less than x less than pi. So let's take that and calculate b sub k, k equals 1 to infinity, right? Just calculate all those b sub k's, and that's not going to be difficult, is it? Remember though, as before, we have to break the integral up into a left side and a right side, the way we did before, and you're going to get the answer we had before, okay? But that's a good place to start here. And I would also like us, we know that, and then we actually, that'll be the convincer as far as this, but we can go directly from these expressions to these, or the other way around. Let me consult the clock. Rather have you guys do it or I do it. Maybe I'll get started. I'll get you started on it. It's a good thing. So the second problem is show derive or prove the real form of the Fourier series. In other words, show that those formulas are true if the ones on the left are true. And there's a couple of ways we can tackle that, because we can go in either direction. One thing we can do is take either of these and express, in fact, yeah, why not? I'll get you started on this. This is a good one. We can express these cosine and sine of kx in terms of the complex exponentials. So let's do this. So we have a sub k is equal to 1 over pi minus pi to pi f of x, but now we're going to plug in cosine of kx in the form e to the I kx plus e to the minus I kx over 2 dx. And you'll do the same thing for the sine with b sub k, and it'll be e to the I kx minus e to the minus I kx over 2 times I. Okay. But let's just continue with this one and see where it takes us. Eventually we'll have a bunch of facts about this and we'll put them all on one page. Okay. But right now we're just working our way through. So we have 1 over 2 pi, brought the 2 out there, minus pi to pi f of x e to the I kx dx plus 1 over 2 pi minus pi to pi f of x e to the minus I kx dx. So that's what a sub k is. Well, that's interesting. What are we looking at here? Apparently, a sub k is equal to c sub k plus c sub minus k. Right? Do I have it up there? Yeah, see. C sub k. In fact, not so fast. This one is c sub minus k. Keep the order here. C sub minus k plus c sub k. Well, that is to say that this a sub k is equal to c sub k plus c sub k complex conjugate. And you can do the same thing for b sub k, right? And then it's only a couple more steps to show that this entire sum here is equal to this one. And that a sub 0 divided by 2 is kind of trivial, because a sub 0 divided by 2 here is the same thing as c sub 0. Okay, so yeah, this was a start, and that's a good problem. Then you'll have this, you know, so what's up here on the board, you'll have shown, and that's a good place to leave it. I do want to also, at the next time, which will be after our exam actually, assign one more of these integrations. They're kind of interesting. You can do a whole bunch of them, but we'll do one more. But good, we'll leave it at that for now, and see you guys next time.